Okay. Right. So let's start with the definition of a differential equation. I mean, you gotta know what that is first, right? So it's just an equation containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables. This is said to be a differential equation. So basically an equation full of derivatives in basic English, right? Now there's different types. Main thing we need to talk about is, so there's definitely need to worry about and ideas here. It's going to be type, order, and linearity. So in the homework and in the book, they're going to ask, okay, is this a linear differential? Is this a, what type is it? Is it a, and of what order? So that's going to keep coming up. So let's first talk about let's see here, where is the definition? Let's talk about type. Okay, so type. So if a DE, I'm gonna try to shorten this so I don't write so much, contains only ordinary derivatives, and I'll explain what I mean by that in just a second, of one or more unknown functions with respect to a single variable then it is an ordinary differential equation, which we will call ODEs. Okay, so that's the first type. So basically just, oops, somebody waiting in the waiting room. So if it's all just basic derivatives with respect to, let's say there's a derivative with respect to x and y. I'm sorry, derivative of a function x and a function y with respect to t. Both of them are respect to t. Then that would be an ODE. Okay. And we'll do in a couple examples in just a second. Okay, now the easy one to spot for PD is, as long as they have a partial derivative, then it's a PDE, but let's just make sure we're legit about it. So an equation involving partial derivatives. Are you guys familiar with partial derivatives? Do you remember? Or have you ever seen them? Of one or more. Let's see. One or more unknown functions. Of two or more independent variables. It's an equation involving partial derivatives of one or more unknown functions of two or more independent variables. This is called a partial differential equation. We're not going to do too much partial in this class, mainly because it requires a lot of numerical methods and they can't be solved straight up. A lot of PD is usually involves coding and computer type solutions. Anyway, so some quick examples as to what is a ODE. So something simple like this guy here. See how it's derivative of x with respect to t plus derivative of y with respect to t equal to 2x and y, right? So since they are both respect to time, this is an ODE. Very, very simple, right? So in the homework, they're going to ask you, okay, what type is it? Or is it linear or is it not linear? Okay, we'll talk about linearity in just a second. This is part A, I guess. Part B would be anything that has a partial in it. So the partial derivative with respect to u over the partial derivative, partial derivative of u with respect to x. So the second derivative. Is everyone familiar with this partial notation? Okay. Let me know if you don't, if you've never seen that before. Okay, partial u over partial y. Okay. I'm assuming you guys know what I'm talking about. You guys seen partials. So as soon as you see a partial, obviously this is not an ODE. Nothing crazy, right? Any questions on how to determine if it's a PD or ODE? Yes. Sorry, what were you saying?
Oh, I said no.
Oh, okay, thanks. All right, let's move on to order then. Order is the easiest one to tell, in my opinion. You just look at the number, really, the highest derivative. Let's be official about it. Make sure everything is legit. So order. All right. So the order of an ODE, or actually PDE, same rules, is the order of the highest derivative. So, for example, let me find one. Yeah, this is a good one. It's from your book. Second derivative of y with respect to x plus 5 first derivative with respect to x cubed minus 4y equal to e to the x. Okay, so what is the order of this differential equation? Yeah, it's going to be 2 because it's the highest derivative. So let me right, second derivative. So this is an ODE, right? First of all, you got to make sure what type it is of second order or of the second order. Okay. Well, that's pretty straightforward. I don't think we need too many examples of order. Does that make sense? Okay. All right, let me see. If there's anything else that needs to be said about order? Okay. Also note if you have in the other form with like y prime, y double prime, etc., those would also be the same, right? I'm going to try to stay away from that notation because this notation is going to be a lot more useful for this class. So try to get used to it if you're not already. Anyway. Let's mention something else. This is called a differential form. So m of xy dx plus n of xy dy is equal to 0. I should say of the first order. This is a specific case for order 1. So if you see it in this form and you need to fix it, like for example, let's say you had, I don't know, here's a good one from the book. Y minus x dx plus 4x dy equal to 0. This would be your differential form of the first order. If you want to get it into a differential equation form, you would have to divide both sides by dx, right? So if I divide everything by dx, you agree that I'll end up here, right? You divide by the differential piece, differential dx. Anyway, just in case it comes up, I want you to know that you can treat these as terms, dy and dx. Later on, we'll be separating this on purpose. Sometimes the book, I don't know if it's going to come up in the homework, but in the book, they do mention that solving for dy dx is called normal form. So just a quick note here. Normal form is the following. I don't think I saw it in the homework, but just in case I forgot. In case I forgot a question or something. So dy over dx would be equal to some f of xy function. Okay. And or if it's the second order, it'd still be the same. But this will contain x, y, and a derivative of y. So this is a normal form differential equation of first order and second order. Okay. So if they ask, put this into normal form, they want you to solve for dy dx, which is just, very simple algebra. Okay. So I'm going to skip that example. You guys have any questions so far? I'm going to move on to linearity. Okay. So let me know. There's no real rush here. Okay. So in general, an nth order differential equation is said to be linear if capital F is linear in y, comma y prime, comma dot dot dot, all the way to the nth derivative This means that nth order ODE is linear when all these terms are linear. So every single y must be linear. Okay. To keep it simple, there's no squares, there's no e to the y, there's no sine of y, no sine of y prime, no e to the y prime. Does that make sense what I'm trying to say? These have to be linear, okay? For the okay. So each term must be linear in order for the entire thing to be linear. Some will write this as this left-hand side as capital F of all this, but let's just keep it this way. So this differential is linear if all of these pieces are linear, okay? Let's find some examples. Well, first let me write what nonlinear means just in case it's not clear. A DE, differential equation, is not linear when functions of the dependent variable or its derivatives are nonlinear, which I know sounds kind of silly. That is to say, you have stuff like sine of y or e to the y prime or something like that. Okay, or y squared or something strange. Does that make sense? What linear means? Okay, so sometimes they try to trick you. So if you put it into differential form or normal form, it would be easy to see whether or not it is linear. Sometimes you can just look at it and say, yeah, linear, who cares? But other times you got to do a little algebra to make sure. Okay. You guys cool on this page? And I will be scanning this after class as well, but if you are writing, let me know before I turn the page. There's no rush. Okay, assuming you're good then. If not, let me know. Linear and nonlinear. Okay. So for the next few problems, we will decide if it's linear and then we'll decide of what order. Okay. And I'll go ahead and tell you the types. We're dealing with ODEs. Is this linear? I don't see any weird powers on the y or the dy dx, right? So yeah, it's going to be linear. But we should double check by solving for dy dx, or at least dividing that part out like we did earlier. I think it might be the same question actually. Dy dx. So yeah, I don't see anything strange with the y. I don't see anything strange with the dy dx. This is linear of first order, right? Nothing crazy. Next one, y double prime minus 2y plus y equals 0. Is this linear? And what is the order?
It's linear to the second order.
Yeah. Linear of the second order. Okay. C. Is this linear, and what is the order?
It's non-linear or not linear.
Yeah, it's not going to be linear. Do you guys see why?
The e to the power of x.
No, that was actually fine. This part's okay. What messes it up is there's a y times the y prime here. So this coefficient is nonlinear. And if I try to divide the y out, I'm going to have a negative y power. So the y's need to be power of 1. And it cannot be inside any e's or signs or anything like that. So this right here makes it nonlinear. That makes sense?
Yes.
Yeah, if you see like any kind of weird stuff on the y, that's what you need to be looking at is the y, or the dy dx, or the y prime.
Why is it of the first order?
Because the derivative is the highest that I see is 1, the first derivative. The order depends on the highest derivative. This has 2. This has 1. This also has 1. So is this linear or nonlinear? And what is the order?
Nonlinear.
Now there's the y is inside of a sign, right? We said we can't have that. So yeah, you're right. Non-linear. Second order, because that is the highest derivative, right? Okay. Now let's go ahead and move on. You guys have any questions on linearity? Okay. Let me give you a definition. Solution of an ODE. So any function phi defined on an open interval which we'll call I, and possessing at least n derivatives that are, excuse me, continuous on I, which, when substituted into an nth order ODE reduces the equation to an identity. This is said to be a solution of the equation on the interval. On I. Okay. So basically what you're going to do in the next few examples and in the homework, they're going to say, here's a differential equation, here's a solution. Verify that it is indeed a solution. So you should get something equals something, basically the same thing on both sides, which is what they mean by identity. Oh, wait a second, because it's a little wordy definition. But to put it in plain old English, this is saying that the solution phi on some interval I has to have n derivatives, meaning you can take as many as you like. Hold on, sorry, that's not true. One moment. N would be respected, well, it would be the same as the order. Yeah, so n derivatives, nth order. So it's not infinite derivatives. That's not required. The only functions that have infinite derivatives would be smooth functions, which are pretty common. Like e to the x or sine, those are considered to be smooth. Okay. Example. So verify that the indicated function is a solution of the given differential equation. On this interval. Okay. Part A. So there's the ODE, and then they give you the solution to the ODE. Remember, the solutions are just the functions themselves. And this whole class is going to be about finding the y solution that satisfies the differential. I don't know why I wrote that so weird. That's 1 over 16 x to the fourth. X to the fourth. So we're going to need dy dx, right? I'm going to plug that in. First derivative would be this, right? So plug that in here, plug in the y here, and see if you get equality. If you do, then we're good. Then we're good. Excuse me. Now here, plug in so we're going to get 1/4 x cubed equal to x times 1/16 x to the 4 to the 1/2, right? So 1/2 is a square root, correct? If you square root this nonsense on the inside, what are you going to get? Right? Square root of x to the 4th and square root of 1/16. Do you agree that this is what we get? All right, 1/2 means square root power. 1/2 power means square root. Square root these terms gets you to here. If I multiply by this x, is this indeed equal? So yeah, they're both equal. That is your solution. So that's all you got to do to determine if it's a solution. Okay. You may need to do a lot of derivatives, so keep that in mind. It's going to feel like Cowan doing a bunch of random derivatives when you're verifying. Okay. Any question on this example?
No, Professor.
You guys cool on this page?
Yes.
All right, let me know if one of you are not. Okay, we'll call this part B, I guess. So y double prime minus 2y prime plus y is equal to 0. Y is equal to x e to the x. So first derivative would be a product rule, right? So the answer would be this. We're going to need the second derivative as well. It's right there in order to verify. So this would be that plus this and this, which would be 2ex plus xex. You guys cool with first and second derivatives? Any questions on this? Let's skip some steps. Okay. So plug in y double prime and y prime. Oh, I suppose you need y as well. And y. Then determine if it's equal to 0. So here we go. So double prime was this guy, 2 minus 2 times this. Right, so I plugged in the y double prime, y prime, and the original y. So let's see what we get. So 2ex plus xex. Distribute your -2, that'll give us minus 2ex minus 2xex plus xex. So these are gone for sure. Got 1, 2, and minus 2 of the same term, which will be 0. Y is a solution. Any questions on part B?
No.
Okay. So let me know at any time if something does not make sense. Okay, so let's give you some definitions. Explicit and implicit solutions. Okay, so I'm sure you've heard the terms implicit and explicit when we were talking about functions back in calculus. Just in case you don't remember. Let's define explicit first. A solution in which the dependent variable is expressed solely in terms of the independent variable. Is said to be an explicit solution. Implicit. One second. A relation g of x comma y equal to 0 is said to be an implicit solution of an ODE on I, provided that there exists at least one function phi that satisfies the relation as well as the differential equation. Okay. Any questions on these definitions? I think I'll do one example and that might be it for 1.1. There's some notation we might have to mention, but Okay. Let's move on to something else, I guess. You guys cool on this page?
Yes.
Okay. So let me know. Define some more for you. Particular solution. So a solution of a differential equation that is free of parameters is called a particular solution. Okay. For all real values of C, the one parameter family y equal to C x plus x cosine x is an explicit solution of the following. On the interval I, which is all real numbers. So since C can be anything, they're saying that this is the solution to this differential equation. C can be 0, 1, 2, 3, 4. If I take a derivative, right, notice how this contains a y prime. We know that y is equal to this guy. Y prime would be equal to C plus cosine x minus x sine x, right? Hold on a second. Yeah. So this C can be anything. So depending on C, you'll have a family of solutions. Okay. Let me find a nice grapher to show this. Okay. Yeah. So this is a solution to the differential if C is 1, right? Now if C is equal to 2, then it's this guy. If it's C is equal to 0, then it'd just be this one, right? If C is negative, so creating a family of solutions here. Looks kind of trippy. Anyway, so C will be probably determined by initial condition. In this case, I just want you to know that it is a family and C can vary. So a particular solution would be if C was equal to 0, like just one of them, right? Like we say, oh, you know what? The only one I care is this particular solution. When C is 0, that is the definition of particular. Okay. There's some condition that dictates C. Even though there's an infinite number of solutions, this let C equal 0 and a particular solution is y equal to x cosine x. That's pretty much it for 1.1. So it's all about definitions and the main idea for differentials. You guys have any questions? Now we'll stop the lecture here.